So, good morning. In our last class, we have been discussing about FIR filter designing by Fourier series method without using any windows. In this class, we will be discussing about the similar thing, that is FIR filter designing by Fourier series method, but over here we will be using windows. Okay. So here you will find that some of the steps they are common. The first two steps they are common. So first we have to draw the frequency response, then we have to calculate the impulse response. Okay, and from there, in the previous case, what we were doing, we are going directly jumping to calculate the Z transform, and then we were realizing the filter. Okay, herein we will not directly jump into this step. However, there are two intermediary steps. What we have to do after we have calculated the impulse response, we have to calculate the window function Wn. Okay, we have to calculate the window function, and then we have to calculate h dash n, which is basically a multiplication of hn and wn. hn and wn. So this multiplication, through this multiplication we will get h dash n, and that h dash n we have to use to calculate the exact the transfer function. Okay, so this is the subtle difference. So first what we will do, draw the frequency response. From there you apply the formula what we have discussed, and from there you calculate the impulse response, and then depending upon the filter characteristics we have to draw or calculate the window coefficients. Then in the next step we have to calculate h dash n, which is nothing but the multiplication of hn and wn, and then we have to use that h dash n to calculate the transfer function of the system, and then we will go for the realization. Okay, till now we have not gone into the realization part, which we will be discussing a bit later. Okay, so what are the types of windows? If you see the first five, they are quite common windows. Okay, so what happens over there? So the most simplest type of window is the rectangular window. Then we have Bartlett window, which is also regarded as the triangular window. Then we have Blackman window, Hamming window. Okay, so in all of these five types of windows, you see the formula over here, it is fixed. Okay, the formula over here is fixed. Then we have another window, another window which is regarded as the Kaiser window. Over here, this formula is not fixed and it varies with the filter characteristics. Okay, so in one way, what happens if we are using the filters, the windows 1 to 5, then you have a fixed formula. You put in the parameters, and after putting the parameters, you will be able to calculate the window functions, and you just go and multiply it. Okay, whereas in the Kaiser window, you have to look into the filter characteristics. From there you have to calculate these window parameters, and then you will be able to get the window coefficients. Okay, so herein if you see in the time domain sequence, windows functions, they are the time domain sequence and they are given by wn, and it varies from 0 to m minus 1. This m is nothing but the length of the filter. So m minus 1, it is basically the order of the filter. Okay, so in the rectangular window, if you see, it is having a rectangular passband like structure. In triangular window or the Bartlett window, you are having a triangular shape. In Blackman, window, you will be having this Gaussian type shape. In Hamming window, you will be having another type of Gaussian type shape, and in the Hamming window, you will be having another type of Gaussian shape. Each of these shapes, they have their own advantages and disadvantages. We will not go into that. Okay, you can go through any of the textbooks, and the corresponding formulas, it has been given. So here there was a mistake, so I have corrected the mistake in this equation over here on the right hand side. Okay. Now let's look into the numerical. Design a low pass filter using rectangular window by taking 9 samples of WN and a cutoff frequency of 1.2 radians per second. Okay. So when we talk about 9 samples of WN, so 9 means it is the length. L is equal to 9, N is equal to 9 minus 1, 8. So we are basically talking about a filter which is having an order of 8. Okay. So in the first step, we will be calculating the HD omega, what we did in our previous cases also. This is equal to e to the power minus j omega alpha for the what you call frequency range of minus of omega c to omega c. Okay. In the previous case, if you see, we have given an amplitude of 1. Here also, if we try to find out the amplitude would be 1. However, we have done a certain tweaking in the formula, and I would say why we have done. In this case, when we are using the window, if you look into the window, it is starting at n equals to 0 and it is going up to the order n, right? Now in the previous case, in the numericals where we have done or designed the FIR filter using without using the what you call this window functions, we have taken the n values from negative to positive. Okay, so you can do it over here also, but to keep the matter very simple, what we will do, we will only consider the window functions and the filter hn values in the range of 0 to n. Okay, otherwise you have to remember in both the cases, both minus n to minus n by 2 to plus n by 2 region, whatever the values would be there, you have to remember that, right? And also the you have to calculate the values of 0 to m minus 1 or capital M, right? So you have to remember the things, this window functions for both the cases. To make the life simple, what we will do, we will only consider the window functions in the range of 0 to capital M. Okay, otherwise you could have done it in the previous way also. Okay, so if you see, we are having this thing, we have designed or we have calculated the what you call the frequency response of the filter. Okay, what should be the frequency response of the desired filter, in fact, right? In the step 2, see, we have applied the same formula. Okay, so here it was hd omega into e to the power j omega n. So hd omega we have discussed that we will put as e to the power minus j omega alpha. Okay, so if you try to simplify this thing, you get e to the power j omega n minus alpha and then if you further simplify it, you get sine of omega c n minus alpha divided by pi of n minus alpha. Now what is this alpha? Alpha is nothing but L minus 1 by 2, which is equal to 4. Okay. Omega c we are already given with the cutoff frequency 1.2 radians per second. So this 1.2 radians per second is the frequency. So you can put it over here. Alpha, you know, it is 4, it is a constant, and it is dependent on the order of the filter, order or the length of the filter, right? So n, what we have to do, we have to vary it from 0 to 8. So you just vary the values of n and you get the this hn values. Okay. Now herein, if you see, when n is equal to 4, our this term it would become 0, also the denominator it would become 0. So due to that reason, when we are calculating h of 4, we have to apply the L Hospital's rule. In the previous case, since we are going from the negative to the positive, and in between the central value was the 0, n equal to 0, so it was automatically at n equals to 0, we were putting the L Hospital's rule. However, in this case, since the middle point is shifted, exactly, is shifted to a specific n value, so at that n value we have to apply the L Hospital's rule. Okay, otherwise you will not be getting the answer. Okay, it will become infinite, the values would become infinite, right? So up to this point our answer is same, or our numerical is similar. Okay, the process is similar. Then what we said in the step 3, we discussed about we have to calculate the wn values. We have to calculate the wn values. Here we are using rectangular window. So rectangular window, they have an amplitude of 1. Okay, and what should be the n values? N values would vary from 0 to 8. So that means W0 equal to W1 equals to W2 equals to W3, and so on up to W8, we get a value of 1. After this, what should be our next step? HD dash n, it is equal to HDN multiplied by Wn. So h of 0 multiplied by W0, W0 is 1, h of 0, we are getting a value of minus of 0.08. So we will be getting h of 0 as minus of 0.08. Similarly, h of 8 also we will be getting minus of 0.08. And that's why we are getting 1 plus z to the power minus 8. Okay. I hope every one of you know why this is 1 and why this is minus 8 we have taken, right? Because x0 into z to the power 0, this is 1, and then we are having h of 8 into z to the power minus 8, right? That's why we are getting these coefficients h of 0 and h of 8, they are same, hence we have taken it common. Similarly, for the other values also we will be getting something like this. Okay. Now coming to the next question, design a band pass filter to pass frequencies in the range of 1 to 2 radians per second using Hanning window with L equal to 5. Okay, so here what we have, HD omega equals to this thing, and then omega C1 to omega C2, it will be allowing the frequency components to pass through. Similarly, we will get two components, minus of omega C2 to minus of omega C1. and here omega c1 to omega c2. Okay, how we got? This we have already discussed, but still I am telling you. So this is omega c1, omega c2. So this is minus of omega c1, minus of omega c2. So when we are putting the integral omega c2 to omega c1, omega c2 to omega c1, then omega c1 to omega c2. Okay, clear? Then just solve it. It's pretty simple. Separately you get this kind of function. Then omega c1 is given as 1 radian per second. This is 2 radians per second. Your L minus 1 by 2, L is given as 5. So alpha is given, you just put the values. So since L is equal to 5, N is equal to 4, so our N values, it will vary from 0 to 4. Okay, so you calculate the values by doing that. And here we are given with Hanning window function. So the Hanning window function is this one. So we can calculate this Hn in this fashion also. This equation has been put over here and over here also. So you can directly put the N values and you get the Hn values directly. Again at h of 2 we have to apply the L hospital rule, because 4 by 2 it is 2. So at 2 at alpha value we have to apply the L hospital's rule, and from there we will be able to get this equation, transfer function. Okay. Then instead of Hanning window, if I would have given you Hamming window, you would have used this equation. If I would have given Blackman window, you would have used this thing. So for exam purposes, I would ask you to remember these four rectangular. You don't have to remember anything. It's one. This Hanning, Hamming, and Blackman. These three are very commonly used in biomedical signal processing. So these three equations you should learn by heart, and numericals will be coming from here. Okay. And practice. Please practice. If you don't practice, it will be difficult for you to perform in the examination. Now, there is another method which is regarded as the frequency sampling method. Okay, so by the frequency sampling method we can design the filters. So let us see how we can design that. So let's see, over here it's given, design a low pass filter with the following specification: cutoff frequency of 500 Hz, sampling frequency of 2000 Hz, and order of the filter is 10. Okay, so the first step over here is the normalization of the frequency. In the normalization of the frequency, we have already discussed omega c equals to 2 pi fc by fs, so it comes out to be pi by 2. Okay, then determine the transfer function. So h of k, frequency it is being given by k, so h of k equals to 1 in the range of 0 modulus of omega of 0 to pi by 2 and 0 otherwise. So determine the locations and amplitudes of the samples. Okay, so this is important what we want to do. So if you see over here, we have put the frequency responses. Okay, so it starts from 0 and it ends at 2 pi. Okay, it starts at 0 and it ends at 2 pi. Okay, so our cutoff frequency, it is at pi by 2. So if you see the dotted lines, this is the ideal natured frequency response. So in the ideal nature frequency response, we will be having this dotted line thing, and again from here we will be having the dotted line thing. Okay, so let me draw it in the red line with red lines. Okay, it will be easier for you. So these are the pass bands. So in the pi by 2, if you calculate it in decimal here, so it comes out to be 1.57. At pi it is 3.14, and 3 pi by 2 it is 4.71, and 2 pi it is 6.28. We also know the point at 0 and point at 2 pi, they are same. They are same, right? So we need to calculate 11 points, or we have to place 11 points within this 0 to 2 pi. In this 0 to 2 pi. So at what distance you will put these points? So that is being given by this function delta, which is equal to 2 pi by n plus 1. That means 2 pi by 11. Okay. And what locations you want to put, that would become k delta, which is nothing but 2k pi by n plus 1. So you have the k values. We know that the k value will be varying from 0 to 11. So 0, you will be getting some value. If you put k value of 1, you will be getting another value. So 0.57, the rest are basically the multiplication of this 0.557 multiplied by 2, multiplied by 3, and so on. And you get certain values. Now if you see, the first point is 0, k delta value is 0. The last point is 6.28. So either we will take 0 or we will take 6.28. So we will definitely take 0 because we are starting from there. So we will strike this off. Okay. So that will not be counted now. Now if you see, at pi by 2, we are having 1.57, and that is the cutoff frequency, and that is the ideal FIR filter which we want to design. But we have a limitation that we are only having some specific number of points. Okay. Now I am changing the color of this pen. So if you see, what is the position of this k delta value? 0. Is it within 1.57? Yes. The first pass band is 0 to 1.57. We have to look into that. So 0.57, it is within this range. 1.14, it is within this range. From point 3 onwards, it is having a value of 0. Okay. And until one point, again, if you see 3 pi by 2, it is having a value of 4.71. So this 4.57, it is outside the range. Okay, but 5.14, it is within the range. So we will be taking this 9, 10. So how many points we are basically getting? 0, 1, 2, 9, 10. So in total we are getting 5 points. Okay, and the other points in between, they are being rejected. Okay, so that means if you see, h of 3 equals to h of 4 equals to h of 5 equals to h of 6 equals to h of 7 equals to h of 8, it is having a value of 0. Okay. The next step is calculate h cap k. Okay. So it is given by h cap k is given by e to the power minus j 2 pi by n plus 1 alpha k. Okay, alpha is 5. Okay, so in the first case k is 0, n plus 1 you know it is 11, alpha is 5. What is the only variable? No, the only variable is k. Just put the values of k. H of 0 it will be 1, h cap 1 you will be getting this value, h cap 2 you will be getting this value, then after that we get h cap 9, h cap 10. So you are able to calculate all these values now, right? Then from here we have to find h of n. Okay, and for this the formula is h of n is equal to 1 by capital N plus 1 h cap 0 plus 2 of real value of summation of k equals to 1 to L minus 1 h cap k multiplied by e to the power j pi j 2 pi k n divided by n plus 1. Okay, so here L minus 1 by 2 is 5, n plus 1 is 11. We have just put the values. Okay, you have all these values from here, then you just have to take the values and solve it, and if you get, see over here what you get, n minus 5, n minus 5, some values are there, e to the power j 2 pi by 11 n minus 5 and e to the power j 4 pi by 11 n minus 5. Okay, now when you get this is basically e to the power j theta equals to cos theta plus j sin theta, but our formula is that we only need the real component, so only the cos theta components will be taken. So you see only the cos theta components are taken, and from there we can get the hn values. Okay, now once you get this hn values, then you perform the z transform, and then we can go for the implementation of the filter. Okay, so these are some of the methods uh, which you need to do, and we will cover it up to this much today. In the next class we will be covering this Kaiser window. Okay.